Yay!
Yay! Another common problem you might see is instead of a velocity function, maybe they give you a velocity graph, velocity against time graph, in which the velocity can be doing some kind of crazy things. Suppose you have something like this. So here's a plot, just a simple plot of velocity and time, right? Time is in the x and velocity is in the y. And I just kept the numbers kind of easy and small. So time just goes from 0 to 10 seconds. And then the velocity is like up to, 4, plus 4 and minus 4 meters per second. Minus 4 is down here. Okay. And then maybe there's some questions you can answer about this graph. Like, for example, what is the acceleration between 2 and 6 seconds? Well, what we're going to do is use the definition of acceleration, right? That's sort of one of our kinematic formulas. Really, it's just the definition of acceleration. Ooh, it's a definition. So put the third equal sign there. So we just need to know the change of the velocity divided by the change in time. And let's be careful. A is delta V over delta T. What is that? Delta always is final minus initial, or delta T. Okay, at the end of that interval, at the 6 seconds, what is the V? It's minus 4, right? So we got to be careful. Minus 4 minus, what was it at the beginning? It looks like 1, 2, 3, 4 up there. And then what's the total change in time from 2 to 6 seconds? 6 minus 2 is 4. Right? So minus 4 divided by 4. So that's going to be minus 8 divided by 4, or minus 2 meters per second squared. Okay, the point is that by taking the slope of the velocity curve between, or velocity line between a couple of points, that's the acceleration, right? It's rise over run. Which is also, right, that's like and if it was a smooth function like we had before, that would be the derivative. The derivative is the slope of the function at a particular point. So it all kind of fits together. Okay, so between any two points on those lines, you should be able to get the acceleration just by taking how much the velocity changes within that time. Another thing that we can answer is stop and change direction. Did the particle stop and change direction? Okay, you got to be careful because this is a plot of velocity, speed, right? You might think that maybe where it's horizontal, the thing is stopped, but that's not true. Where it's horizontal, like here at the end between 8 and 10, that's where the velocity is constant. That's where it keeps going the same amount of speed. So where does it stop? It stops when v is 0. So it stops wherever it crosses the x-axis, right? At that point and that point. That's where it stops and turns around. So one of those points is 4, and then the other one is somewhere between 7 and 8. If you know the slope, you could probably figure it out. All right, and then the third thing that's commonly asked in problems like this is if it starts at 0, starts at position 0, where is the final position? So where did the particle end up, right? It does this crazy thing. It speeds up, slows down, stops, goes backwards, and so on. Finally, at the end of 10 seconds, where is it? We should be able to find out where this thing is. All right, what are we going to do? Well, one formula is probably not going to be good. We can't just plug a number into one thing and then get the answer because the velocity is changing all over the place. So instead, what we're going to have to do is to do this sort of piecemeal. There's a couple of different ways you can do it. One way you can do it, although this isn't, here's a possible way that you could do it. Look over here. We know that the change in position is the velocity times the time, right? Now, the velocity is the x, and the time, I'm sorry, the velocity is the y, and the time is the x. So look over here. In that last bit, the velocity is a constant 2 over 2 seconds. So just in that last piece, if you go 2 meters per second, a constant 2 meters per second for 2 seconds, how far do you go? You go 4, right? Well, that's just the area of that little square, right? It's 2 by 2. So if you were doing this on graph paper, one thing that you could do, which is perfectly fine, is that you could count boxes. You could count little graph squares. And then the total of those graph squares with the amount that's on top of the x-axis is going to be positive, below the x-axis is going to be negative. You total all those up, and that'll tell you how far the particle has gone. And what I'm really saying is, and you kind of know this if you've had calculus, is that it's the area under the curve, right? It's easy to see that the area under the horizontal line is just, you just count those boxes. But it's the same thing here. If you count this area, it's harder to count the boxes because there's like partial boxes. But if you counted the area that's colored in there, that would be the area under the curve, right? Which is the integral, which is kind of what we did last time. What we're going to do, though, instead of counting boxes, because if you, for the lines that cut through boxes, it's kind of hard to count them. They're sort of fractional boxes. So instead, let's do it piecewise using a kinematic formula. Okay, let's use this. I also know that delta x is v initial plus 1/2 a delta t squared, right? So let's do it piecemeal. So let's do delta x equals. There's going to be a bunch of different pieces. Let's do that first piece. What is that first piece? Delta x for the first piece is going to be v initial. What's our v initial? Well, that line starts at 2, right? So it's going to be 2 times, what is our delta t? We're just going to keep going until the velocity changes. So it's a straight line up to 2 seconds. So let's do that first piece. So 2 times 2, and then this is going to be plus 1/2. What is the acceleration during those first 2 seconds? Well, I go from 2 to 4, right? So I increase my speed by 2 over 2 seconds, so that a is going to be 1. The slope of that line is 1. So this is going to be times 1 times 2 squared, right? I'm just filling in numbers in that formula. Okay, that's the first piece. Second piece. The second piece is that long line that goes from 2, 3, 4, 5, 6 seconds. That's going to be 4 seconds long, right? So let's do that piece. So I have to add in the next piece. And the next piece is going to be, what is my initial? It's v initial. What's my initial speed at the beginning of that piece? Well, it's up at 4. So this is going to be 4 times, my delta t is going to be 4. Minus, look, my acceleration is going to be negative, right? And we've already found out what it is. It's minus 2. So this is going to be minus 1/2 times 2 times 4 squared. Neat. Okay, third piece. Third piece is going to be from the t equals 6 down at the bottom, and it rises up to v equals 2 at 8 seconds, right? So what is my initial speed? It looks like it's going to be minus 4, and my elapsed time is going to be from, let's see, 6 to 8. So it's going to be 2 plus, the acceleration is going to be positive. And what is the acceleration here? In 2 seconds, it looks like I'm going from minus 4 to plus 2. So that's going to be a slope of 3, right? So it's going to be 1/2 times the acceleration is 3, and then this is 2 squared. Oh, running out of room. Oh, but this is the last bit. So this is going to be v initial for the last horizontal bit. V initial is going to be 2 at the beginning of this. 2 times 2 plus, that's going to be it, right? Because the A, what is the acceleration of that piece? 0, because the V is horizontal. It's not changing at all. So I don't even need to, I don't even need to work. Well, let me just write it down, just so. Plus 1/2 times 0 times 2 squared. Okay, well, it's going to be 0. All right, so now what we got to do is just plug in these numbers, and let's see what the total displacement is for each piece, and then the total overall. So let's see, 2 times 2, the first bit, 1/2, so that's going to be 2 times 4 plus 2. This is going to be 6. A good exercise is to plot this out on graph paper, count the boxes here in that first region, and you should be able to convince yourself that there are 6 boxes, 6 colored in boxes there. Some are partial, right? But if you total it all up, it should be 6. How about the next one? The next one is that next piece, 4 times 4, 16 minus, looks like 16 minus 16, 0. Ooh, this makes sense. Look, let me color in with a different color. We want the area under the curve, right? Well, how much area is under the curve? There's a triangle here above, and then the same triangle below. So those two things are going to cancel out, right? So I go one way and then the other. And so, yeah, for that piece, I get actually 0. I get no displacement at all for that piece. Okay, next, I have minus 4 times 2. So it's minus 8 plus 2 times 3 is 6. So here, this is going to be a minus 2 for that piece. And then finally, we already said for that last horizontal piece, I should get a 4. 2 times 2 is 4. So there's my displacements for all the pieces. So all you do is you add them all up. 6, 0, minus 2, and 4. So it looks like our delta x at the end turns out to be 8 meters. So at the very end of all this crazy business, our particle should be like 8 meters down, positive 8 meters down the x-axis. Neat. So if you have these functions of velocity and time, you can pull out a lot of information from them. You can get the acceleration, and then you can get the total displacement. And the best way that I know of to attack this is to do it like that. Just do it piecewise for every constant acceleration. All right, on to another one.